You might think a bullet train is fast, or even the speed of sound, shattering the air with a sonic boom. But out there in the vast, silent expanse of the cosmos, the universe operates on an entirely different scale of velocity, where speeds so extreme they warp reality itself become the norm. Picture this: light zipping around Earth's equator 7.5 times in just 1 second, or a neutron star spinning so rapidly its surface moves at nearly a quarter the speed of light, flinging entire mountains into space with centrifugal force. These aren't science fiction, they're real, measurable, and utterly staggering phenomena that redefine what fast even means. This is a realm where particles surf shockwaves at nearly light speed, where black holes slingshot stars like cosmic pebbles across galaxies, and where entire clusters of galaxies race away from us faster than the very light they emit. And here's the thing, these aren't rare exceptions. The universe is brimming with these extremes, each one a testament to the raw, unbridled power of physics operating at its most spectacular. Today, we're diving deep into 30 of the most mind-bending speed records the cosmos has to offer, from the blistering jets erupting from supermassive black holes to the eerie quiet of particles moving so fast they outpace time itself. Why does this matter? Because speed isn't just about getting from point A to point B, it's the language the universe uses to tell its grandest stories. It shapes galaxies, forges elements, and even dictates the ultimate fate of everything we know. And as we unravel these cosmic speed demons, you'll start to see the invisible forces stitching reality together in ways that'll leave you awestruck. So buckle up, we're about to take a journey where the slowest thing we'll encounter is your average shooting star, and even that will feel like standing still compared to what's coming next. Let's start with the ultimate speed limit of the universe, light itself. Racing through the vacuum of space at 299,792 kilometers every single second, light doesn't just move fast, it defines fast. According to Einstein's theory of relativity, this isn't just a speed limit for light, it's the cosmic speed limit for everything. No object, no signal, no information can ever outpace it. It's as if the universe itself put up a giant stop sign etched into the fabric of reality. But here's where it gets even stranger. The speed of light isn't just about distance and time, it warps them. Imagine two astronauts, one stays on Earth while the other zooms through space at near light speed. When the traveling astronaut returns, they'd have aged less than the one who stayed behind. This isn't science fiction, it's time dilation, a real phenomenon proven by atomic clocks on fast-moving jets ticking slightly slower than those on the ground. The faster you go, the more time itself stretches and bends around you. And then there's the sheer scale of cosmic distances. Even at light speed, crossing our galaxy would take 100,000 years. The nearest star system, Alpha Centauri, 4.3 years one way. That's why when we look at distant galaxies, we're not just seeing space, we're peering back in time. The light from Andromeda, our closest galactic neighbor, takes 2.5 million years to reach us. By the time it arrives, we're witnessing a snapshot of the past, a cosmic fossil frozen in light. This universal speed limit shapes everything from the way particles interact to the fate of the cosmos itself. Without it, the universe as we know it wouldn't just be different, it would be unrecognizable. Light speed isn't just a measurement, it's the rulebook for reality. Now imagine a star not gently drifting through space like our sun, but hurled outward with such violence that it's essentially a celestial cannonball. Meet hypervelocity stars, cosmic fugitives rocketing through the void at speeds so extreme they're on a one-way trip out of our galaxy altogether. Take S5 HVS1, a rogue star clocked at over 1,700,000 kilometers per second, so fast it could cross the entire United States in less than a second. That's over 300 times the speed of our solar system's journey around the Milky Way. How does a star even reach such insane velocities? The answer lies in the gravitational jaws of a supermassive black hole. Picture a binary star system, two stars orbiting each other, wandering too close to the monster at the heart of our galaxy, Sagittarius A star. As one star gets captured, the other is violently slingshotted outward like a stone from a catapult, reaching speeds that defy comprehension. The energy behind this ejection is so colossal. These stars don't just escape their home systems, they break free from the Milky Way's gravitational grip entirely, destined to drift forever in the bleak emptiness between galaxies. Astronomers first spotted these interstellar outlaws in 2005, but S5HV-S1's discovery in 2019 was a watershed moment. Racing through space at nearly 0.2% the speed of light, its trajectory traced back directly to the galactic center, confirming the black hole ejection theory. What's astonishing is that this star isn't some lightweight. It's a hydrogen-burning main sequence star, twice as massive as our Sun. Where's it headed? Right now, it's already tearing through the outskirts of the Milky Way's halo, and in about 100 million years, it'll cross into intergalactic space, becoming an orphan of the cosmos. But here's something even wilder: hypervelocity stars aren't just galactic ejections. They're time capsules. Their speed and trajectory let astronomers reverse engineer the Milky Way's gravitational field, mapping the invisible dark matter that shapes our galaxy's structure. And they're not alone. Dozens of these runaway stars have been identified, each with its own blistering speed and tragic backstory. Some may even carry planets with them. Imagine a world orbiting a star moving so fast that constellations would streak across its sky like comet trails. If any life existed there, it would witness the ultimate cosmic exile, watching the Milky Way shrink into a distant smudge of light, forever receding into the darkness. If hypervelocity stars seem fast, wait until you meet the universe's ultimate spinning tops, pulsars. These neutron stars take speed to another level entirely, rotating so quickly their surfaces can reach a quarter of light speed. Take Pulsar J1748-2446 AD, the fastest spinning pulsar we've ever discovered, whirling at an incomprehensible 43,000 revolutions per minute. At that rate, it could complete a full spin in just 0.0014 seconds. To put that in perspective, if Earth spun that fast, our planet's equator would be moving at about 1/6 the speed of light, and everything not bolted down would be flung into space. What makes this possible? It all comes down to neutron stars having some of the most extreme physics in the cosmos. When a massive star collapses in a supernova, its core compresses into a city-sized object so dense that a single sugar cube-sized chunk would weigh as much as Mount Everest. All that mass packed into such a small space means gravity is mind-bendingly strong, but so is the conservation of angular momentum. Just like an ice skater pulling their arms in to spin faster, the collapsing star's rotation accelerates drastically as it shrinks. The original star might have rotated once every few weeks, but by the time it becomes a neutron star, it's spinning hundreds of times per second, the real mind-blowing part. These speeds aren't just theoretical, they warp spacetime itself. At 24% light speed, the pulsar's equator experiences extreme relativistic effects. Time moves slower there compared to its poles, and the incredible centrifugal force stretches the star into an oblate shape, flattening it like a cosmic pancake. But here's the kicker: despite spinning fast enough to tear ordinary matter apart, pulsars don't fly to pieces because their gravity is over 200 billion times stronger than Earth. It's the ultimate tug-of-war, centrifugal force trying to fling material outward while gravity crushes it back down. And pulsars don't just spin, they're cosmic lighthouses. Their magnetic fields, trillions of times stronger than Earth's, funnel radiation into beams that sweep across space like a searchlight. Every time a beam passes Earth, we detect it as a pulse, hence the name pulsar. Some of these beams flicker with such precise regularity they rival atomic clocks, making pulsars nature's most accurate timekeepers. What's even wilder is that Pulsar J1748 isn't alone. Dozens of millisecond pulsars spin at mind-melting speeds, often revved up even further by stealing matter from companion stars. These cosmic dynamos push the limits of physics, proving that when it comes to speed, the universe always finds a way to outdo itself. Black holes aren't just cosmic vacuum cleaners, they're also nature's most powerful particle accelerators. Take the supermassive black hole at the heart of Galaxy M87, famous for the first ever image of a black hole's shadow. But what's even more astonishing is the jet screaming from its poles, a concentrated beam of plasma stretching 5,000 light-years into space, moving at 99.9% the speed of light. That's so fast, if you could ride this jet, you'd circle Earth 7 times in the blink of an eye. How does a black hole, an object so dense not even light can escape, launch material outward at near light speed? The secret lies in its chaotic magnetic fields. Picture this: as matter spirals into the black hole's accretion disk, it heats up to millions of degrees, creating a swirling soup of charged particles. The black hole's immense gravity isn't just pulling material in, it's also twisting spacetime itself, winding magnetic field lines into a cosmic slingshot. These fields act like colossal railroad tracks, channeling some of the infalling matter away from the event horizon and accelerating it along the black hole's rotation axis. The result, a jet so energetic it can punch through entire galaxies. The M87 jet isn't just fast, it's unimaginably powerful. The energy it carries rivals the output of 1,000 Milky Ways combined. And it's not alone. Astronomers have spotted similar jets across the universe, from smaller stellar mass black holes to quasars billions of light-years away. Some jets even outshine their host galaxies, visible across cosmic distances. What's truly wild is that these jets aren't just shooting out random particles, they're sculpted with eerie precision. Magnetic fields collimate the plasma into narrow beams, keeping them focused over thousands of light-years. It's like a cosmic fire hose with no nozzle, yet the jet stays razor straight, defying the tendency of explosions to spread out. But here's the kicker: relativistic jets aren't just spectacular light shows, they shape the universe around them. When these jets slam into surrounding gas, they trigger shock waves that can ignite star formation or, conversely, sterilize entire regions of space, preventing galaxies from growing too large. They're the ultimate double-edged sword, creators and destroyers on a galactic scale, and the particles in these jets, they're not just moving fast, they're experiencing physics at its most extreme. At 99.9% light speed, time for them slows to a crawl compared to the outside universe. A single minute on one of those particles could mean years passing elsewhere. It's a stark reminder that in the cosmos, speed doesn't just change where you're going, it changes how time itself flows. Even light speed has its overachievers, particles so fast they make black hole jets look sluggish. Meet cosmic rays, especially the record-breaking "Oh my God" particle, detected in 1991, hurtling through space at 99.99999999999% the speed of light. To grasp how absurdly fast that is, if this particle raced a beam of light across the Milky Way, it would lose by less than the width of a single atom. The energy packed into that single subatomic speck, equivalent to a baseball smashing into your hand at 100 kilometers per hour, except concentrated into something 1,000,000 billion times smaller. Where does such unimaginable velocity come? That's the cosmic mystery scientists are still untangling. These particles don't originate from gentle processes. They're likely forged in the most violent events imaginable: supernova shockwaves, colliding neutron stars, or jets from active galactic nuclei. Some might even be survivors of theoretical dark matter annihilation. But here's the catch, even our most extreme astrophysical engines struggle to explain the oh my god particle's energy. It carries 40 million times more punch than anything our largest particle colliders can produce, defying known acceleration mechanisms. The real shocker, these particles are everywhere. Thousands strike Earth's atmosphere every second, though most are far less energetic. When they collide with air molecules, they trigger cascades of secondary particles, a phenomenon first discovered over a century ago but still not fully understood. Some theories suggest these ultra-high-energy cosmic rays might be iron nuclei stripped of electrons, while others propose exotic particles beyond the standard model. What's certain is their speed warps physics itself. At such velocities, time dilation means these particles experience existence in slow motion. A single second for one could equate to centuries passing in the rest of the universe. Detecting them is another feat of ingenuity. The oh my god particle was spotted by the fly's eye detector in Utah, which captured the ultraviolet glow of its atmospheric collision. Modern observatories like the Pierre Auger Array now scour the sky for these rare events, tracing their paths backward to potential sources. Yet their origins remain elusive, scattered across the sky with no clear galactic hotspots. This suggests they might be extragalactic hitchhikers, accelerated across mind-boggling distances by forces we've yet to comprehend. Why should we care? Because these particles are nature's ultimate physics lab, probing energies we'll never replicate on Earth. They might hold clues to quantum gravity, hidden dimensions, or entirely new particles. Some could even be relics from the Big Bang, frozen in near light-speed flight for billions of years. Every time one streaks through a detector, it's like receiving a postcard from the universe's most extreme environments, written in a language we're still learning to decode. Think the fastest cosmic objects are lone stars or particles. Think again, entire galaxies can become supersonic projectiles when clusters collide. Take the Bullet Cluster, two galaxy groups smashing together at a staggering 10 million kilometers per hour. That's so fast, the shockwave alone heats gas to 100 million degrees, glowing fiercely in X-ray telescopes. But here's the twist. This collision didn't just create a cosmic firework, it handed us the first direct proof of dark matter's existence. When astronomers first studied the Bullet Cluster in 2004, they expected chaos. Galaxies are crammed with stars, gas, and dust, so a high-speed crash should leave everything tangled. But something bizarre happened. The visible galaxies passed right through each other almost unscathed, like ghosts. Meanwhile, the hot gas between them, detectable by its X-ray emissions, slammed together so violently it created a bow shock visible across space. This alone was mind-blowing, but the real revelation came when astronomers mapped the cluster's gravity using gravitational lensing. The mass wasn't where the gas or galaxies were. Instead, two huge invisible halos had drifted ahead of the collision, carrying most of the system's weight. That discrepancy was the smoking gun for dark matter. Ordinary matter, the gas that glows in X-rays, interacts strongly, slowing down during collisions. But dark matter doesn't interact with light or itself. It's influenced only by gravity. So when these clusters collided, the dark matter components barely noticed, coasting through the chaos while the gas lagged behind. It's like watching two crowds of people run into each other in a fog. The visible people, gas, get stuck, bumping and slowing, while invisible marathoners, dark matter, keep sprinting ahead, revealed only by their footprints warping the ground beneath them. The Bullet Cluster's speed was critical here. Only a collision this violent could separate dark and normal matter so dramatically. Slower mergers might have kept them mixed, hiding the evidence. But at 10 million kilometers per hour, the contrast was unmistakable, a cosmic dissection proving dark matter isn't just theoretical. It's real, it's massive, and it shapes the universe's structure on the grandest scales. What's wilder, this isn't unique. Since the Bullet Cluster, astronomers have spotted other dark matter labs in colliding clusters like MAX J0025.4-1222 and the Musket Ball cluster. Each one reinforces the same truth: dark matter outweighs visible stuff 5 to 1, and its ghostly nature only reveals itself in extremes. These collisions are more than wreckage. They're cosmic experiments showing us a hidden universe we're only beginning to decode. Supermassive black holes aren't just lurking at galaxy centers. Some are cosmic fugitives rocketing through space like intergalactic outlaws. Take 3C186, a black hole with the mass of 1 billion suns caught red-handed fleeing its host galaxy at 7.5 million kilometers per hour. That's so fast it could travel from Earth to the Moon in under 3 minutes. Hubble's images reveal the smoking gun, a brilliant quasar blazing behind it like a comet's tail, the unmistakable signature of a black hole on the run. How does something billions of times heavier than our Sun get kicked into interstellar exile? The answer lies in the universe's most violent merger. When two galaxies collide, their central black holes eventually spiral together, locked in a gravitational dance. As they orbit closer, they emit ripples in space-time called gravitational waves, not evenly, but in a lopsided burst. Picture two ice skaters spinning while holding hands. If one suddenly lets go, the other gets flung away. That's exactly what happened here. The final moments of the black hole's merger unleashed a gravitational wave kick so powerful it ejected the newly formed monster like a cosmic cannonball. What's astonishing is the energy behind this ejection. The recoil force needed to hurl 3C186 at this speed equals the equivalent of 100 million supernovas exploding simultaneously. That's not just moving a black hole, that's overcoming the gravitational pull of an entire galaxy. The quasar tail we see is the aftermath of this chaos. As the black hole plows through intergalactic gas, it superheats the material, creating a 35,000 light-year long streak of plasma, a celestial breadcrumb trail marking its path of destruction. But here's the twist: this runaway isn't just a curiosity. It's rewriting our understanding of galaxy evolution. Black holes and their host galaxies grow in lockstep, but 3C186 proves they can be violently separated. Its original galaxy, now 2,000 light-years behind, shows signs of trauma. Stars flung into disorderly orbits, gas clouds ripped apart. For the first time, we're witnessing the aftermath of a black hole divorce, proving these mergers aren't always tidy cosmic marriages. And it's not alone. Astronomers have spotted dozens of candidate rogue black holes, some even faster, suggesting this might be a common and spectacular part of the universe's life cycle. The real puzzle: what happens next? A black hole moving this fast can't be recaptured by its galaxy. It'll drift forever in the void, a nomad feeding on whatever gas it encounters. Billions of years from now, it might even collide with another galaxy, starting the cycle anew. And that quasar tail, eventually, it'll fade, the last beacon of a black hole that refused to stay put. A reminder that even the universe's most massive objects can become fugitives. If you think Mercury's orbit is blisteringly fast, prepare for a world where a single year is shorter than a typical workday. Kepler 70b, a planet that screams around its star at 1.5 million kilometers per hour, completing a full orbit in just 8.5 hours. That's so fast, if you lived there, you'd celebrate 2 birthdays before lunch and witness 3,000 sunrises in a single Earth year. To put that into perspective, Mercury, the speed demon of our solar system, moves at a comparatively sluggish 47 kilometers per second, taking a leisurely 88 days to orbit the Sun. Kepler 70b doesn't just break records, it obliterates them. What could possibly propel a planet to such insane velocities? The answer lies in its horrifyingly close orbit. This scorched world circles its host star, Kepler 70, at a distance 10 times closer than Mercury is to our Sun. so close, in fact, that its surface temperatures exceed 6,700 degrees Celsius, hotter than some stars. At that range, the star's gravitational pull is ferocious, whipping the planet around like a slingshot on steroids. The forces at play here are so extreme, Kepler 70b shouldn't even exist. Conventional planet formation theories suggest gas giants can't form this close to their stars, yet here it is, a Jupiter-sized world somehow surviving an environment that vaporizes rock. The strangest part, this planet might not be alone. Its star, a former red giant that's now shrunk into a hot subdwarf, likely engulfed other planets as it expanded before collapsing back. Kepler 70b could be the sole survivor of a planetary massacre, its orbit tightened by gravitational chaos as its siblings were consumed. Or perhaps it migrated inward after the star's contraction, defying the usual rules of celestial mechanics. Either way, it's a cosmic oddity, a planet dancing on the edge of annihilation, where a single misstep would mean being torn apart by tidal forces or swallowed whole. But here's the real kicker. Despite its terrifying speed and proximity, Kepler 70b isn't the fastest possible. Some theoretical ultra-short period planets could orbit even quicker, with years lasting mere hours. These worlds push the limits of what's physically possible, where a planet's own orbital velocity nearly matches its escape velocity, teetering on the brink of being flung into space. Kepler 70b is a reminder that when it comes to cosmic speed records, the universe always finds a way to one-up itself, turning what we think we know about planetary physics into a thrilling game of hold my atmosphere and watch this. You might think Earth feels perfectly still beneath your feet, but we're actually part of a cosmic joyride, one that sends our entire solar system hurtling through the Milky Way at 828,000 kilometers per hour. That's over 230 kilometers every single second, fast enough to circle Earth's equator 6 times in the time it takes to brew a cup of coffee. To put that into perspective, we're outpacing the fastest human-made object, NASA Parker Solar Probe, by more than 200 times, but here's where the scale gets mind-boggling. In just one day, our solar system travels a staggering 19 million kilometers through the galaxy, equivalent to 50 round trips to the moon. Stack that up over a year, and we've covered nearly 7 billion kilometers, farther than any Voyager spacecraft has ever journeyed. Yet despite this breakneck speed, we don't feel a thing. Why? Because everything around us, our sun, neighboring stars, even the galaxy itself, is moving together in this grand gravitational dance. It's like being on a train traveling at a constant speed. Unless you look out the window, you'd never know you were moving at all. This motion isn't random. We're orbiting the Milky Way's core, much like Earth orbits the Sun, only instead of taking 365 days, a single galactic year lasts roughly 230 million Earth years. The last time we were in this position, dinosaurs ruled the planet and flowering plants were just evolving. Our path isn't a perfect circle either. Gravity from nearby galaxies like Andromeda tugs at us, creating subtle ripples in our trajectory over cosmic timescales. What's truly wild is how little this speed affects us. The Milky Way's vast size means our solar system's motion is smooth, like a surfer gliding on an ocean wave. No turbulence, no sudden stops, just the steady pull of hundreds of billions of stars collectively shaping our path. Yet this motion isn't meaningless. It's the reason we see constellations slowly shift over millennia, and why future astronomers will gaze up at a nightscape utterly unrecognizable from our own. But here's the twist. Even at this speed, we're cosmic slowpokes compared to some stars. Hypervelocity stars leave us in the dust. Our solar system's velocity is just a fraction of what's possible when the universe really puts its foot down. So next time you feel like you're standing still, remember, you're actually racing through the galaxy faster than any human invention could hope to match. Right now, an unstoppable cosmic train is barreling toward us. Andromeda, the closest spiral galaxy to our Milky Way, racing through the void at 402,000 kilometers per hour. That's faster than most asteroids, a speed so immense it could cross the entire United States in under 20 seconds. And here's the unsettling part: this isn't some distant hypothetical. It's happening right now, with Andromeda covering the space between us at a rate that would make even hypervelocity stars seem sluggish. But don't panic just yet. This galactic collision won't happen for another 4 billion years. When it does, the merger will be less of a violent crash and more of a slow, mesmerizing dance. Picture two vast flocks of birds, each numbering in the hundreds of billions, swirling together in an intricate ballet where individual stars almost never collide. That's because despite their staggering size, galaxies are mostly empty space. The real fireworks will come from gravity's invisible hand, warping their shapes beyond recognition. Supercomputer simulations paint an astonishing future. First, Andromeda's gravitational pull will stretch the Milky Way's disk, twisting spiral arms into chaotic streamers of stars. Over millions of years, the two galaxies will swing past each other, then loop back in a series of ever-tightening orbits. Each pass will fling stars into wild new trajectories, some ejected into intergalactic space, others flung toward the merging cores. By the time the dance is done, the Milky Way and Andromeda will have merged into a single, colossal elliptical galaxy, unofficially nicknamed Milkdromeda. What's wild is how different the night sky will look during this slow-motion spectacle. As Andromeda draws nearer, it'll swell from a faint smudge into a brilliant disk rivaling the full moon. Then, as the galaxies intertwine, new star-forming regions will ignite across the sky, painting it with nebulae far brighter than Orion's sword. Eventually, the familiar band of the Milky Way will dissolve, replaced by a glowing haze of stars scattered in every direction. But here's the twist: Earth will likely survive unscathed. Our solar system might get punted to the galaxy's outskirts or even ejected entirely, a cosmic castaway adrift between stars. Yet even that pales next to another revelation. We're not the only ones in for a shake-up. Andromeda's satellite galaxies, like the Triangulum Galaxy, will join the fray, turning this into a three-way merger. It's a reminder that in the grand scheme, galaxies aren't static islands, they're dynamic beasts, constantly evolving through collisions that reshape the universe itself. And this isn't unique. Hubble's deep-field images show galaxy mergers were commonplace in the early universe, sparking bursts of star formation and feeding supermassive black holes. In a way, Andromeda's approach is just the universe doing what it's always done: recycling, rebuilding, and rewriting the cosmic landscape on scales too vast for human minds to fully grasp. The only difference: this time we're along for the ride. Humans might not be the fastest creatures in the universe, but we've built machines that push the boundaries of speed in ways nature never imagined. Take NASA Parker Solar Probe, currently the fastest human-made object ever, screaming through space at 692,000 kilometers per hour. That's fast enough to zip from New York to Tokyo in under a minute, or circle Earth's equator 13 times in a single hour. But here's what's truly astonishing: this tiny spacecraft didn't achieve that speed through brute force alone. It's been playing an interplanetary game of gravitational pinball, using Venus like a cosmic slingshot to steal momentum and hurl itself ever closer to the Sun. Each time the probe swings by Venus, the planet's gravity tugs on it, shaving off just enough orbital energy to tighten its spiral toward our star. Think of it like a roller coaster dropping into a dive, except instead of tracks, it's riding the curvature of spacetime itself. These gravity assists have propelled Parker to speeds once thought impossible for human technology, shattering records with every pass. But velocity isn't even its most jaw-dropping feat. To survive this mission, the probe had to endure temperatures hotter than lava, flying through the Sun's corona where temperatures spiked to over 1 million degrees Celsius. That's where its revolutionary heat shield comes in, a carbon composite umbrella just 11 centimeters thick. yet capable of keeping the spacecraft's instruments at room temperature despite the inferno outside. If you scaled up its performance to something familiar, it's like standing in front of a blast furnace hot enough to melt steel, while holding a pane of glass that keeps your backside as cool as a spring breeze. The shield's reflective white coating reflects 99.9% of the sun's radiation, and its ability to withstand temperatures twice as hot as lava comes from a material originally designed for missile nose cones. What's wild is that Parker isn't just breaking records, it's rewriting solar science. Flying closer to the sun than any object in history, it's unraveling mysteries like why the corona is hundreds of times hotter than the sun's surface, or how solar winds accelerate to supersonic speeds. Every data packet it beams back is gold dust for physicists, helping predict solar storms that could knock out power grids on Earth. And the craziest part, Parker's not done yet. With 2 more Venus flybys scheduled, it's on track to hit even higher speeds, peaking at an almost inconceivable 700,000 kilometers per hour. That means by the time this mission ends, a human-made object will have touched the atmosphere of a star while moving faster than any natural object in our solar system. Not bad for a species that only left the ground in powered flight little over a century ago. Imagine a wind so fierce it could clear out an entire galaxy in the blink of a cosmic eye. That's the reality of quasar winds, supercharged cosmic hurricanes blasting through space at 26 million kilometers per hour, like the ones erupting from SDSS J1106+1939. These aren't gentle breezes, they're tsunamis of energy capable of vaporizing gas clouds light years across and reshaping the destiny of galaxies themselves. At the heart of this phenomenon lies a supermassive black hole gone rogue. As matter spirals into its accretion disk, friction heats it to millions of degrees, turning the surrounding gas into a seething plasma. But instead of just swallowing everything, the black hole's intense radiation and magnetic fields channel some of this material outward in jets, and here's where things get explosive. The pressure builds until it erupts in a colossal wind, hurling charged particles at speeds approaching 3% of light speed. That's like detonating 1 million nuclear bombs every second, continuously for millennia. What makes these winds truly extraordinary isn't just their speed, it's their reach. The SDSS J1106 wind stretches over 1,000 light-years from its source, sweeping up enough material to build 40 times our sun's mass every year. To put that in perspective, if this wind replaced Earth's atmosphere, it would strip our planet down to bare rock in nanoseconds. But here's the cosmic irony. These destructive forces might actually be galactic lifesavers. Astronomers believe quasar winds act like a universal thermostat. Without them, galaxies would grow too massive, too fast, hoarding gas that would otherwise form stars. The resulting mega-galaxies would burn through their fuel in a frenzy of supernovas, leaving behind dead husks. But these winds pump the brakes, ejecting just enough material to regulate star formation. It's a delicate balance. Too little wind and galaxies overeat, too much and they starve. Evidence of this balancing act is etched across the cosmos. In galaxy clusters like Perseus, X-ray telescopes spot vast cavities carved by ancient quasar winds, ghostly bubbles where star formation was abruptly halted. Other galaxies show chemical fingerprints proving their gas was recycled by these outflows, enriched with heavy elements before being blown clear. Even our Milky Way might owe its stable growth to past quasar activity, though our central black hole is mercifully quiet now. The real kicker, these winds might solve one of cosmology's biggest puzzles. For decades, astronomers wondered why the universe isn't littered with far more giant galaxies than we observe. Quasar winds could be the missing piece, nature's way of hitting the cosmic reset button, ensuring galaxies don't grow beyond their means. As SDSS J1106 demonstrates, Sometimes the most violent forces in the universe aren't just destroying, they're sculpting, regulating, and maintaining the fragile equilibrium that makes galaxies like ours possible in the first place. Gamma-ray bursts don't just break speed records, they redefine them. These cosmic detonations unleash jets of plasma expanding at 99.9999% the speed of light, so close to the universal speed limit that if they were any faster, they'd break physics itself. Picture the energy of 1 billion suns concentrated into a beam no wider than a straw, then fired across the universe like a cosmic blowtorch. That's what telescopes detected from GRB 080319b in 2008. A burst so powerful its afterglow outshone every star in its host galaxy combined. The mechanics behind these jets are as terrifying as they are fascinating. When a massive star collapses into a black hole or neutron stars merge, the resulting explosion channels energy into twin beams along the rotation axis. Magnetic fields tighter than any lab could produce coil around these jets, acting like particle accelerators the size of solar systems. Electrons surfing these fields get whipped to near light speed, emitting gamma rays as they spiral. A process so efficient it converts matter into energy with nearly 100% efficiency. The numbers defy belief. In just 10 seconds, a single gamma-ray burst can release more energy than our Sun will radiate across its entire 10 billion-year lifespan. But here's what's truly humbling. We're only seeing the tip of the cosmic iceberg. Because these jets are so narrowly focused, astronomers estimate we miss 99.9% of gamma-ray bursts simply because their beams aren't pointed at Earth. The ones we do detect, like the record-setting GRB 221009 last year, often originate from billions of light-years away, meaning their light has traveled across most of cosmic history before triggering our satellites. The aftereffects are equally mind-bending. As these ultra-relativistic jets plow through interstellar gas, they create shockwaves that glow for weeks in X-rays and radio waves. Some leave behind macronovae, kilonovae on steroids, where heavy elements like gold and platinum are forged in quantities large enough to seed entire galaxies with precious metals. It's no exaggeration to say the gold in your jewelry likely came from one of these cataclysmic events billions of years ago. What's perhaps most startling is how recent our understanding of these phenomena is. The first gamma-ray burst wasn't identified until 1967 by military satellites monitoring nuclear tests, and for decades afterward, astronomers debated whether they originated in our galaxy or the distant universe. Today, we know they're the birth cries of black holes and the universe's most extreme particle accelerators, natural laboratories testing physics under conditions we'll never replicate on Earth. Yet mysteries remain. Why do some bursts last milliseconds while others linger for minutes? How exactly do particles reach such insane energies without violating known physics? And crucially, what would happen if one occurred nearby? A gamma-ray burst within a few thousand light-years could strip Earth's ozone layer, triggering mass extinctions. Thankfully, the odds are astronomically low, but the fact that we can even contemplate such cosmic power puts our place in the universe into stark perspective. These aren't just distant curiosities, they're reminders of how small and fragile our corner of space really is. Most galaxies exist in clusters or groups, gravitationally entwined with neighbors, but not MCG plus 01-02-015. This loner holds the title of fastest spinning spiral galaxy ever observed, rotating at 1.8 million kilometers per hour, so fast its outer stars should be flung into the void. Yet against all odds, this cosmic maverick holds itself together while drifting through one of the universe's emptiest regions, a desolate stretch called the Boötes Void, where galaxies are so scarce, its nearest neighbor might as well be on another planet. What makes this speed demon so fascinating isn't just its velocity, it's the defiance of expectations. Normally, galaxies this isolated should be sluggish, with little external influence to stir them into motion. But MCG plus 0, 1 minus 0, 2 minus 0, 1, 5 whirls with the ferocity of a galaxy 10 times its size, hinting at a turbulent past. Astronomers suspect it might be a survivor, the last remnant of a shredded galaxy cluster, its rotation sped up by ancient gravitational tugs from long-vanished siblings. Alternatively, it could harbor a supermassive black hole whose violent outbursts injected energy into the galactic disk, setting the whole structure spinning like a top. The galaxy's isolation adds another layer of mystery. The Boötes void spans 330 million light-years with fewer than 60 galaxies scattered across its expanse. To put that in perspective, if our Milky Way sat in such emptiness, the night sky would appear nearly starless, with Andromeda barely visible as a faint smudge. Yet somehow, against this barren backdrop, MCG plus 0, 1 minus 0, 2 minus 0, 1, 5 maintains a perfect spiral structure, an improbable feat without neighboring galaxies to shape its form through gravitational interactions. Stranger still is how it retains its gas. Most isolated galaxies should have exhausted their star-forming material eons ago, yet this one shows signs of ongoing stellar birth. One theory suggests it's cannibalizing tiny, undetected dwarf galaxies' cosmic snacks that occasionally drift too close. Others propose its extreme spin generates shockwaves that compress gas clouds, triggering new star formation in a self-sustaining cycle. Whatever the explanation, this galaxy defies the stereotype that solitude equals stagnation, proving even the loneliest corners of the universe can host dynamic, high-speed marvels. By studying its motion, astronomers gain insights into dark matter's role in galactic spin. The fact that MCG plus 0, 1 minus 0, 2 minus 0, 1, 5 hasn't torn itself apart implies an immense dark matter halo anchors it, invisible scaffolding weighing hundreds of times more than its visible stars. That halo might also explain its bizarre trajectory. While the galaxy rotates rapidly, it's also moving through the void as a whole at an unusual angle, as if something unseen is pulling it sideways. This cosmic speedster challenges our understanding of how galaxies evolve in isolation. It's a reminder that the universe loves exceptions, and that sometimes the most extreme record holders aren't found in crowded stellar metropolises, but drifting alone in the darkness, spinning faster than physics seems to allow. At the heart of an unassuming system 12,000 light-years away, two dead stars are locked in the fastest orbital dance ever witnessed. Cancri, a white dwarf binary circling each other at 1.8 million kilometers per hour. That's so rapid they complete an entire revolution in just 5.4 minutes. To grasp how absurdly fast this is, consider that our moon takes 27 days to orbit Earth. These stellar remnants whip around each other so quickly, you could watch them complete a full loop in the time it takes to microwave popcorn. The physics behind this dizzying speed is even more mind-bending. White dwarfs are the collapsed cores of dead stars, incredibly dense objects packing a sun's worth of mass into a sphere the size of Earth. In Cancri's case, the two dwarfs are separated by a mere 150,000 kilometers, less than half the distance from Earth to the Moon. At that proximity, their gravitational pull is so intense, space-time itself can't keep up. The system emits gravitational waves, ripples in the fabric of reality predicted by Einstein, at a rate so high, they're carrying away enough energy to shrink the orbit by 7 millimeters every year. Here's the cosmic irony: those gravitational waves are both the system's death sentence and its greatest legacy. As the dwarfs lose energy, they spiral inexorably closer, destined to merge in roughly 300,000 years. But until then, they serve as a living laboratory for extreme physics. Their orbit is so precise, it acts like a cosmic clock ticking with unrivaled accuracy, so reliable that astronomers have used it to confirm gravitational wave theory with near-perfect agreement. The discovery of H.M. Cancre's breakneck speed was almost accidental. Initially spotted in X-ray emissions, astronomers assumed it was a single object until they noticed its light dimming and brightening every 5 minutes. The realization that this flickering came from not one, but two stars eclipsing each other at incomprehensible velocity rewrote our understanding of compact binaries. Now it stands as one of the strongest indirect proofs of gravitational waves years before LIGO direct detection. What's truly staggering is how much this system pushes the limits of known physics. The gravitational forces at play here stretch matter to its breaking point, with each white dwarf warping its companion into a teardrop shape. Tidal interactions between them generate enough heat to produce X-rays detectable across the galaxy, while their combined gravity creates a time dilation effect, making clocks on these stars tick slower than anywhere else in the Milky Way. Yet for all its extremes, H.M. Cancre isn't just a cosmic oddity, it's a glimpse into the future. Countless similar binaries likely exist across the universe, silently spiraling toward collisions that could ignite supernova or form exotic hybrid stars. Some might even collapse directly into black holes. By studying this system, we're witnessing the prelude to one of the universe's most violent acts, a slow-motion collision where the speed isn't in the impact, but in the dizzying dance that leads there. Somewhere beyond the edge of our cosmic horizon, something massive is pulling, an unseen force so powerful it's dragging entire galaxy clusters toward it at 3.2 million kilometers per hour. This eerie phenomenon, known as dark flow, was first detected in 2008 when astronomers noticed hundreds of galaxy clusters mysteriously streaming in the same direction, as if caught in a gravitational current no one could explain. The oddest part, this motion defies everything we know about cosmic expansion. The universe isn't just stretching uniformly, it's being tugged sideways by something lurking in the shadows. The leading suspect, a structure so enormous it dwarfs the observable universe. Picture this, beyond what our telescopes can see, there might be a supercluster of galaxies with the mass of tens of thousands of Milky Ways, an unimaginably dense knot of matter whose gravity reaches across billions of light years to influence us. But here's the catch: according to standard cosmology, nothing that massive should exist. The Big Bang's afterglow suggests matter was distributed relatively evenly, leaving no room for such a colossal anomaly. Yet the evidence keeps piling up. The Planck satellite's data revealed the dark flow extends at least 2.5 billion light-years, hinting that whatever's out there isn't just big, it's unlike anything in our current maps of the cosmos. Then there's the wilder theory. This gravitational pull might originate from another universe entirely. In the multiverse hypothesis, our universe is one bubble in an infinite cosmic foam, each with its own physical laws. If a neighboring bubble universe brushed against ours during its birth, the collision could have left an imprint, a gravitational wake still dragging matter toward it like a ship following the trail of an unseen iceberg. It's speculative, sure, but not impossible. The math suggests such an interaction could create precisely the kind of large-scale flow we're observing. But before we jump to parallel universes, there's another contender: primordial magnetic fields. These hypothetical relics from the Big Bang's first moments could stretch across the cosmos, weaving invisible lines of force that nudge galaxies en masse. Think of it like a hidden subway system beneath the universe, with galaxy clusters as commuters all heading downtown. While less dramatic than multiverses, this idea fits with known physics. Magnetic fields of this scale could theoretically form during cosmic inflation, the universe's explosive growth spurt. The real puzzle isn't just explaining dark flow. It's grappling with what it means for our understanding of reality. If the pull comes from beyond our observable universe, it implies the cosmos is far less uniform than we thought, with structures so vast they redefine large scale. If it's a magnetic effect, we're missing a fundamental piece of early universe physics. And if it's a parallel universe, well, that would be the most profound discovery in history. proving we're not just part of a universe but a multiverse. Until we have answers, dark flow remains one of cosmology's greatest mysteries, a ghostly hand tugging at the fabric of reality, reminding us how much we still don't know about the cosmos beyond our horizon. At the very heart of our galaxy, where gravity twists space-time into knots, there's a star dancing on the edge of oblivion, S4714, the fastest known star in the Milky Way. This stellar speed demon rockets around Sagittarius, a star, our supermassive black hole, at a blistering 24,000 kilometers every single second. That's 8% the speed of light, fast enough to cross the Atlantic Ocean in the time it takes to snap your fingers. But what makes this star truly extraordinary isn't just its velocity. It's the daredevil trajectory it follows, swinging so close to the black hole that its orbit would fit inside our solar system with room to spare. Picture this, a star weighing more than our Sun, streaking through space on an oval-shaped path so extreme that at its closest approach, it skims just 12 astronomical units from the black hole's event horizon. That's about the distance from the Sun to Saturn, except instead of a serene gas giant, there's a gravitational monster 4 million times more massive than our Sun, warping space so severely that time itself slows down for the star as it screams past. The forces at play here are so intense, S4714 completes a full orbit in just 7.6 years, compared to our solar system's sedate 230 million-year galactic journey. How does a star survive such a treacherous orbit? The answer lies in its incredible speed. Just as a motorcycle can ride vertically inside a circus globe of death by outrunning gravity, S4714's velocity keeps it from being torn apart or swallowed whole. But this balancing act comes at a cost. Every close pass subjects the star to tidal forces so powerful they strip away layers of its atmosphere, leaving a glowing trail of stolen stardust in its wake. Astronomers discovered this celestial speedster using decades of painstaking infrared observations, cutting through the galactic dust that obscures our view of the Milky Way's core. What they found rewrote the rulebook on stellar dynamics. Previously, scientists thought stars couldn't orbit so close to a black hole without being shredded, yet here's S4714, defying expectations and opening new questions about how such extreme systems form. One theory suggests it might have been part of a binary star system that ventured too close, with one star getting captured while S4714 was slingshotted into its current death-defying orbit. The star's breakneck speed offers more than just cosmic spectacle, it's a unique probe of Einstein's general relativity. As S4714 whips around Sagittarius, a star, its orbit gradually rotates, tracing a spirograph-like pattern called Schwarzschild precession. This effect, predicted by relativity but rarely seen so clearly, provides one of the most precise tests yet of how gravity behaves in the most extreme environments. Every loop this star completes helps scientists refine their understanding of black holes, dark matter, and the very fabric of space-time. Yet the most mind-bending realization might be this: we're witnessing a cosmic race against time. Given enough orbits, even this star's incredible speed won't save it from eventually spiraling into the black hole, but that won't happen for millennia. Until then, S4714 will keep setting new records, pushing the limits of what we thought possible, and reminding us that when it comes to cosmic speed demons, the universe always has another surprise up its sleeve. The universe isn't just expanding, it's doing so at a speed so precise and relentless, it rewrites our understanding of distance and time. Hubble's law, one of the cornerstones of modern cosmology, tells us that galaxies are racing away from us at 73 kilometers per second for every megaparsec of space between us. To grasp how bizarre this is, picture a loaf of raisin bread baking in the oven. As the dough expands, every raisin moves away from every other raisin, not because they're actively traveling, but because the space between them is stretching. Now imagine that loaf is the entire cosmos, and those raisins are galaxies hurtling apart at speeds that grow with every scrap of distance. But here's where it gets strange. While galaxies appear to be moving faster than light at vast distances, a phenomenon called superluminal recession, they're not actually breaking any cosmic speed limits. Unlike objects moving through space, which are bound by Einstein's universal speed limit, the expansion of space itself can carry galaxies apart at any speed. It's like dots on a stretching rubber sheet. No dot is moving faster than the others relative to the sheet, but the sheet's stretching creates the illusion of impossible velocity. This expansion rate, known as the Hubble constant, is anything but constant. When Edwin Hubble first measured it in the 1920s, he had no idea it would spark a century-long debate. Today, we've pinned it down to that 73 kilometers per second per megaparsec, but with a twist, quantum physics suggests a different value entirely. The cosmic microwave background, the afterglow of the Big Bang, implies a slightly slower expansion rate of 67 kilometers per second per megaparsec. This discrepancy, dubbed the Hubble tension, has astronomers scrambling. Either one of our measurements is flawed, or the universe is playing by rules we haven't discovered yet. Consider the implications. If space stretches faster in some regions than others, it could mean dark energy. The mysterious force driving cosmic acceleration isn't uniform. Some theorize it evolves over time, growing stronger or weaker in ways we can't yet predict. Others suggest entirely new physics, like hidden dimensions or exotic particles altering gravity's grip on cosmic scales. The wildest possibility, our universe might be colliding with another in a higher dimensional space, warping local expansion rates in ways we're only beginning to detect. Yet amidst the theorizing, one truth stands out. The universe's expansion isn't just a distant abstraction. It shapes everything. Given enough time, galaxies beyond our local group will vanish over the cosmic horizon, their light stretched beyond detectability. Distant civilizations, if they exist, will become forever unreachable, not because they're too far, but because the space between us is growing too fast. It's a humbling reminder that speed isn't just about motion, it's about the fabric of reality itself, stretching and twisting in ways we're only beginning to fathom. When two neutron stars collided in a galaxy 130 million light-years away, they didn't just create ripples in space-time. They hurled a storm of precious metals into the cosmos at a staggering 30% the speed of light. The event, detected in 2017 and dubbed GW170817, remains the most spectacular fireworks show the universe has ever put on. A kilonova explosion so powerful it forged hundreds of Earth masses of gold and platinum in mere seconds. Imagine a cosmic alchemy lab where the crucible is a sphere of ultra-dense star guts, and the fuel is pure gravitational chaos. The mechanics of this extreme speed start with the neutron, stars themselves city-sized remnants of dead stars, each so dense a teaspoon of their material would weigh as much as a mountain. Locked in a deadly spiral, these objects circled each other thousands of times per second before merging, warping space-time so violently they emitted gravitational waves detectable across the universe. But the real spectacle began in the final milliseconds. As their surfaces touched, tidal forces ripped them apart, flinging a fraction of their material outward in jets moving at nearly a third light speed. The rest collapsed into a black hole, but not before triggering a shockwave that superheated the ejected debris to trillions of degrees. What makes this ejector so special isn't just its velocity, it's what it carried. Neutron star material is nature's ultimate pressure cooker, where atomic nuclei get crushed into exotic, neutron-rich states. When this stuff gets launched into space, those neutrons rapidly attach to atoms in a process called the Rapid Neutron Capture Process, or R process. Within seconds, ordinary elements transform into heavyweights like gold, platinum, and uranium. The numbers defy belief. GW170817 alone may have produced up to 500 Earth masses of gold, enough to gild every planet in the Milky Way. But here's the kicker. This gold isn't just sitting in space. Those high-speed ejector clouds eventually slam into interstellar gas, dispersing their metallic treasure like cosmic confetti. Over millions of years, these enriched gas clouds collapse into new stars and planets, seeding the universe with the ingredients for everything from jewelry to microchips. In fact, most of the gold on Earth likely came from similar neutron star mergers billions of years ago. Every time you hold a wedding ring, you're holding stardust forged in one of the universe's most violent speed demonstrations. The afterglow of GW170817 told this story in brilliant detail. For days, telescopes watched as the expanding debris cloud released more energy than a supernova, glowing first blue from radioactive cobalt, then red as heavier elements like platinum and uranium took over. It was the first time humanity had witnessed the birth of heavy elements in real time, a Rosetta Stone for understanding where the universe's precious metals come from. What's truly humbling is realizing how common this must be. Neutron star mergers might occur as often as once every 10,000 years per galaxy, meaning the cosmos is constantly peppered with these high-speed metal factories. Some calculations suggest all the gold in the universe could have been made in just the first few billion years after the Big Bang, a frenzied era of cosmic collisions that set the table for everything that followed. And the speed, that's the ultimate delivery system. Without those 30% light speed ejector, these heavy elements would fall back into the black hole or clump uselessly around the merger site. Instead, they're launched across galaxies, ensuring no corner of the universe is left without the ingredients for complexity. From the iron in your blood to the platinum in catalytic converters, we're all made of materials that began their journey in explosions moving faster than anything humans could ever hope to build, proof that sometimes the universe's most extreme speeds aren't just about destruction. They're about creation. Most planets take their time orbiting their stars. Mars leisurely strolls around the Sun in 687 days, while distant Neptune takes a glacial 165 years. But TOI 2109b laughs in the face of such cosmic dawdling. This ultra-hot Jupiter holds the record for the fastest known exoplanet year, completing a full orbit in just 16 hours while screaming through space at 850,000 kilometers per hour. That's so fast, if you lived here, you'd celebrate 2 birthdays before Earth even finished one rotation. At this breakneck speed, TOI 2109b isn't just orbiting, it's clinging for survival. The planet orbits so close to its star that gravity has locked it in a death grip, forcing one hemisphere to eternally face the inferno while the other stares endlessly into freezing darkness. This tidal locking creates the most extreme day-night contrast known in planetary science. The dayside broils at 3,500 degrees Celsius hotter than some red dwarf stars, while the night side plunges into a frigid negative 1,000 degrees. The physics behind this hellscape is as fascinating as it is terrifying. TOI 2109b's orbit is just 2.4 million kilometers from its star, 20 times closer than Mercury is to our Sun. At that range, stellar radiation bombards the planet with such intensity that its atmosphere is literally evaporating, trailing a glowing tail of ionized gas like a cosmic comet. The gravitational forces at play are so extreme, they've stretched the planet into a football shape, with tidal bulges flexing its surface thousands of kilometers outward. Astronomers suspect this world wasn't always such a speed demon. Like most hot Jupiters, it likely formed farther out before migrating inward, but unlike others that stabilize at comfortable distances, TOI 2109b just kept falling. Now it's spiraling toward its star at the fastest rate ever observed, losing about 600 meters of altitude every Earth year. within another million years, a blink in cosmic time, it may either crash into the star or be torn apart by tidal forces. What makes this discovery groundbreaking isn't just the planetary extremes, it's what it reveals about the final stages of hot Jupiter evolution. Watching TOI 2109b is like catching a star in the act of devouring its own planet, a process we've theorized about but never seen unfolding in real time. Every observation offers new clues about atmospheric escape, tidal interactions, and the ultimate fate of worlds that venture too close to their suns. The planet's blazing dayside also acts as a natural laboratory for exotic chemistry. At such temperatures, molecules break apart into individual atoms, metals vaporize into clouds, and minerals like corundum, the stuff of rubies and sapphires, might rain from the sky. Some models even suggest the night side could harbor strange superconductors formed under unimaginable pressure and cold. Yet among all these extremes, one question lingers: how did it get so close in the first place? Most migration theories can't fully explain its orbit without invoking multiple planetary collisions or an unusually dense protoplanetary disk. Whatever the answer, TOI 2109b stands as a reminder that the universe loves breaking its own rules, and that when it comes to cosmic speed records, the most fascinating stories often lie at the edge of destruction. The sun's corona isn't just hot, it's a riot of plasma waves moving at speeds so extreme they defy intuition. During solar flares, eruptions of energy send Alfvén waves rocketing through the corona at 145 million kilometers per hour. That's fast enough to cross Earth's orbit in under 15 minutes, a velocity so immense it could fling plasma from the sun's surface to beyond Pluto in just over a day. But these waves aren't just about raw speed, they might hold the key to one of astrophysics' most stubborn puzzles: why the corona, the sun's outer atmosphere, is millions of degrees hotter than the surface beneath it. Picture the sun like a campfire. Normally, you'd expect the air farther from the flames to be cooler, not scorching. Yet the corona blazes at over 1 million degrees Celsius, while the visible surface simmers at a relatively modest 5,500 degrees. For decades, scientists struggled to explain where this extra heat comes from. Enter Alfvén waves, named after Nobel laureate Hans Alfvén, who first predicted their existence in the 1940s. These aren't ordinary ripples, they're magnetic tsunamis, born when the sun's tangled magnetic field lines snap and reconnect, releasing energy that sends plasma surging along their length like guitar strings, vibrating at cosmic frequencies. What makes these waves truly remarkable is how they transport energy. Unlike sound or light waves, Alfvén waves move through magnetized plasma by transferring energy via magnetic tension. Imagine shaking a jump rope tied to a tree. The rope itself barely moves, but the wave races along it at incredible speed. In the corona, this mechanism lets energy traverse vast distances without dissipating, depositing heat far from its source. Recent observations from spacecraft like NASA's Parker Solar Probe have captured this process in action, revealing how these waves cascade into turbulent eddies, dissipating their energy as heat like ocean waves breaking into foam, but at temperatures rivaling volcanic lava. The sheer scale of these events boggles the mind. A single solar flare can unleash Alfvén waves spanning tens of thousands of kilometers, carrying enough energy to power human civilization for millennia. Yet their role in coronal heating isn't just about brute force, it's about precision. The wave's ability to target specific regions of the corona helps explain why the heating isn't uniform, why some areas flare to 10 million degrees while others remain relatively cool. This fine-tuning suggests the sun's magnetic field acts like a cosmic conductor, orchestrating where and how energy gets distributed, but the mystery isn't fully solved. While Alfvén waves explain part of the heating, they likely share the stage with other processes: nanosecond solar explosions called nanoflares, or even interactions between plasma particles. It's a reminder that even something as seemingly familiar as our sun still harbors secrets, its outermost layer crackling with energy we're only beginning to decipher. Every wave detected, every flare analyzed, brings us closer to understanding not just our own star, but the magnetic furnaces lighting up the universe. Most planets and stars rotate with the stately grace of a ballroom dancer, except 2MSSJ 0348-6022, a brown dwarf spinning so fast it makes hurricanes look sluggish. This failed star completes a full rotation in just 1 hour, its surface screaming through space at 320,000 kilometers per hour. That's 10 times faster than Jupiter's already brisk 12-hour day, and so extreme that if this brown dwarf spun any quicker, centrifugal force would literally tear it apart. What makes this speed demon even more astonishing is its size. Although classified as a brown dwarf, a celestial object too massive to be a planet but too small to ignite full stellar fusion, 2MSSJ 0348 is still roughly the diameter of Jupiter. Imagine an object that size spinning fast enough to fling its own atmosphere outward like a cosmic centrifuge. The equator bulges noticeably under the strain, while the poles flatten under forces that would reduce solid rock to molten slurry. How does something so compact reach such breakneck speeds? Unlike stars, which slow down as they age due to magnetic braking, brown dwarfs have weaker magnetic fields, allowing them to preserve their youthful rotation rates for billions of years. This one might have formed from a particularly turbulent gas cloud, inheriting an abnormally high angular momentum. Or perhaps it was spun up by a close encounter with another object, transferring energy in a gravitational slingshot. The comparison to Jupiter is particularly striking. Both objects are gas giants of similar size, yet Jupiter's winds, while powerful enough to swallow Earth whole, move at a sedate 47,000 kilometers per hour compared to 2MSSJ 0348 supersonic maelstrom. If you stood on Jupiter's cloud tops, you'd experience a 10-hour day. On this brown dwarf, the horizon would whip past your field of vision every 30 minutes, daylight and darkness flickering like a strobe light. But speed isn't the only oddity here. The rapid rotation twists the brown dwarf's magnetic field into complex knots, generating auroras thousands of times brighter than Earth's northern lights. These aren't powered by a star like our auroras, but by internal heat left over from its formation, a faint, fading ember of what might have been stardom. What's truly fascinating is what this tells us about the line between planets and stars. Brown dwarfs occupy a mysterious middle ground, and 2MSSJ 0348 pushes the limits of that category. Spin it faster and it might shatter, slow it down and it becomes just another dim, forgettable object. Instead, it dances on the edge of stability, a cosmic top that refuses to stop. Stretching across nearly half the night sky, the Magellanic Stream arcs through space like a celestial river. But this isn't just any cosmic ribbon. This vast trail of gas races around the Milky Way at 1,100,000 kilometers per hour, a silent witness to the violent gravitational ballet between our galaxy and its orbiting dwarfs. What makes this structure so fascinating isn't just its speed. It's the fact that we're seeing the aftermath of a slow-motion collision that's been unfolding for billions of years, leaving behind a filament of gas so massive it could birth millions of stars. The story begins with the Large and Small Magellanic Clouds, two dwarf galaxies circling the Milky Way like moths around a flame. These aren't static neighbors. They've been locked in a gravitational tug of war with our galaxy and each other, their mutual interactions stretching and distorting their gas into the immense ribbon we see today. Computer simulations reveal the drama. As the clouds orbit, the Milky Way's gravity peels gas away from them, while their own gravitational interactions fling additional material into space. The result is a 300,000 light-year long streamer, composed mostly of hydrogen so diffuse it's invisible to the naked eye, yet moving fast enough to circle Earth's equator in under 13 seconds. But the real revelation came when astronomers measured the stream's composition. Its gas doesn't match the Milky Way's instead. It carries the chemical fingerprints of the Magellanic Clouds, rich in elements like oxygen and sulfur forged in their stars. This was the smoking gun proving the stream originated from the dwarfs, not our galaxy. Even more telling, the gas isn't just being pulled, it's being accelerated. As the clouds zip through the Milky Way's halo at 400,000 kilometers per hour, they plow through a thin sea of hot gas, creating a bow shock that superheats and ionizes the stream, giving it the energy to maintain its breathtaking velocity. What's wild is how recent this cosmic theft still is. While the stream's oldest strands may date back 2.5 billion years, new observations show fresh gas still being stripped from the clouds today. The European Space Agency's Gaia mission even spotted stars being tugged loose, proof that the demolition derby isn't over, yet the stream's fate is sealed. Over the next few billion years, its gas will spiral inward, eventually raining down onto the Milky Way's disk in a slow-motion downpour that could fuel new star formation. This isn't just a tale of destruction, it's a preview of the Milky Way's future. The same forces shredding the Magellanic Clouds will one day tear apart even larger galaxies when Andromeda collides with us in 4 billion years. The stream is a living laboratory showing how galaxies grow by cannibalizing their neighbors, stitching themselves together with stolen gas and stars. And for all its immensity, it's just one thread in a vast cosmic web, proof that even the fastest-moving structures in the universe are part of a slower, grander dance, where gravity writes the music and time keeps the beat. Deep in the constellation Puppies, a pair of dead stars perform a gravitational tango so extreme it warps the fabric of spacetime itself. Pulsar J0737-3039, the only known double pulsar system and one of nature's most precise laboratories for testing Einstein's theories. These neutron stars, each more massive than our Sun yet barely 20 kilometers across, whip around each other at 1 million kilometers per hour, completing a full orbit in just 2.4 hours. Their dance is so tight, the entire system could fit inside our Sun with room to spare, creating conditions where general relativity isn't just theory, it's observable reality. What makes this binary extraordinary isn't just its speed, it's the lighthouse-like pulses of radiation that revealed its secrets. As the stars spin, their powerful magnetic fields beam radio waves across space like cosmic metronomes, with one pulsar flashing 44 times per second while its companion ticks along at 2.8 seconds. These rhythmic signals allowed astronomers to track the star's movements with nanosecond precision, uncovering subtle distortions in their orbits that matched Einstein's predictions to within 0.05% accuracy. The system's gravitational waves, ripples in spacetime first detected here indirectly, carry away orbital energy equivalent to the Sun's total output every 150,000 years, causing the stars to spiral closer by 7 millimeters daily. But the real magic happens when one pulsar passes behind the other. Its radio pulses take 87 microseconds longer to reach Earth during these eclipses, not because the path is longer, but because the foreground star's gravity bends spacetime, delaying the signal exactly as relativity predicts. It's like watching a cosmic version of Einstein's elevator thought experiment play out in real time. Discovered in 2003, this system has become relativity's ultimate testing ground. Its orbit's gradual decay provided the first indirect evidence for gravitational waves decades before LIGO direct detection. The way its pulses are delayed and distorted has ruled out alternative gravity theories, while the precise dance of these ultra-dense objects continues to challenge our understanding of extreme matter. Some researchers even use it to hunt for hidden dimensions, analyzing whether gravity weakens at infinitesimally small scales. Yet for all its scientific value, Pulsar J0737-3039 is also a ticking time bomb. In about 85 million years, the stars will merge in a kilonova explosion, likely forming a black hole and briefly outshining every star in the Milky Way. Until then, their relentless waltz keeps broadcasting physics lessons across the cosmos, a masterclass in gravity written in pulses of radio light and the silent tremors of warped spacetime. Asteroids might seem like slow-moving space rocks, but 2021 PH27 shatters every expectation. This city-sized chunk of cosmic debris tears around the Sun at an astonishing 106 kilometers every second. That's nearly 3 times faster than Earth's orbital speed, completing a full revolution in just 113 days despite swinging out farther than Venus at its most distant point. What makes this asteroid's velocity so extraordinary isn't just the raw numbers, it's the physics-defying path it takes, diving closer to the Sun than any known asteroid and experiencing gravitational effects so intense they warp Newtonian expectations. At its blistering closest approach, 2021 PH27 skims within 12 million kilometers of the solar surface, so near that its surface temperatures reach 500 degrees Celsius, hot enough to melt lead. This extreme proximity subjects the asteroid to relativistic effects normally reserved for Mercury, causing its orbit to precess, or gradually rotate, by an unparalleled 20 arcseconds per century. To put that in perspective, Mercury's famous precession, which helped confirm Einstein's theory of general relativity, clocks in at just 43 arcseconds per century. This tiny asteroid's path twists through space like a spirograph on overdrive, offering astronomers a unique natural laboratory to test gravity's limits. The secret behind this speed lies in its elliptical orbit's extreme eccentricity. Like a cosmic rubber band, 2021 PH27 spends most of its time drifting lazily beyond Earth's orbit before plunging sunward in a gravitational death dive, accelerating to peak velocity as the Sun's gravity whips it around like a slingshot. Each close pass imparts enough energy to fling it back into the outer solar system, only to repeat the cycle again and again. This isn't just orbital mechanics, it's celestial Parker, with the asteroid exploiting every gravitational trick to maintain its breakneck pace. Discovered in August 2021 by the Dark Energy Camera in Chile, this asteroid immediately stood out for more than just its speed. Spectral analysis suggests it might be a fragment of a Mercury-like protoplanet from the early solar system, blasted into its current orbit by ancient collisions. Alternatively, it could be a solidified comet nucleus, its volatile ices long since baked away by repeated solar encounters. Either way, its existence challenges standard models of solar system formation, proving some objects can survive, even thrive in orbits once thought too extreme for rocky bodies. But the real cosmic irony, this speed demon's days are numbered. Intense solar heating and gravitational stresses are slowly tearing it apart, with calculations suggesting it might fragment or collide with the Sun within the next million years. Until then, every close pass offers astrophysicists priceless data on everything from general relativity to asteroid composition, all from a rock moving so fast it could cross the continental United States in under 40 seconds. Some galaxies don't just form stars, they explode with them, birthing new suns so furiously they blast their own guts into deep space. Take M82, the iconic starburst galaxy 12 million light-years away, where stars ignite 10 times faster than in our Milky Way. This frenzy births cosmic hurricanes called galactic superwinds, jets of gas screaming outward at 3 million kilometers per hour, fast enough to cross the entire United States in under 2 seconds. These aren't gentle breezes, they're tsunamis of energy hotter than the Sun's core and laced with heavy elements forged in supernovas, spraying the building blocks of planets and life far beyond their home galaxy. The violence begins in M82's core, where dense gas clouds collapse into stars at breakneck speed. But these aren't ordinary stars. Many are colossal blue giants, burning bright and dying young in supernova explosions that rock the galaxy. Each detonation floods nearby space with shockwaves, while stellar winds from massive stars act like cosmic sandblasters, carving cavities in surrounding gas. Combine thousands of these eruptions, and you get a pressure cooker with no lid, a superwind that punches through the galaxy's disk like a geyser, dragging along iron, oxygen, and carbon like cosmic shrapnel. What's astonishing isn't just the speed, it's the reach. These winds billow hundreds of thousands of light years into intergalactic space, far beyond M82's visible boundaries. The Hubble Space Telescope caught this drama in vivid detail, filaments of ionized gas stretching like fiery tentacles, backlit by the galaxy's glow. Some structures resemble smoke from a candle snuffed too violently, except here, the smoke is plasma hot enough to melt diamonds, and the candle is a galaxy-wide inferno. But here's the twist: these superwinds aren't just destructive. They're galactic gardeners, seeding the universe with the ingredients for rocky planets and life. Heavy elements forged in stars like the calcium in your bones or the silicon in Earth's crust would stay locked inside galaxies without these violent outflows. M82's winds ensure they escape, mingling with the sparse gas between galaxies. Over eons, this enriched material becomes raw fuel for future stars and planets, possibly even life-bearing worlds in galaxies not yet born. The numbers defy belief. A single starburst episode can eject over 50 million suns worth of gas, carrying enough oxygen to fill 10,000 solar systems with breathable air. And M82 isn't alone. Galaxies like NGC 2146 and IC10 show similar outflows, each contributing to a cosmic recycling program on the grandest scales. Astronomers call this chemical evolution, the process by which the universe transforms primordial hydrogen into the diversity of elements we see today. What's wild is how these winds shape their surroundings. As they plow into intergalactic space, they create shock fronts that trigger secondary star formation like a snowplow piling up drifts where new stellar nurseries can form. Some models suggest our own Milky Way experienced starburst winds billions of years ago, potentially explaining oddities in its chemical makeup. Even now, traces of ancient superwind material might linger in the galactic halo, a fossil record of past violence written in the language of elemental abundances. Yet the most profound implication lies beyond single galaxies. Superwinds from countless starbursts have likely turned the space between galaxies into a dilute soup of heavy elements, meaning no corner of the universe is truly pristine. Even the emptiest voids might contain stray atoms of iron or gold, gifts from long-dead stars hurled across the cosmos by winds like M82's. It's a humbling thought. The same forces that tear galaxies apart also knit the universe together, ensuring that no star, and perhaps no life, ever truly arises in isolation. Meet the universe's ultimate cosmic predator, PSR J1311-3430, better known as the Black Widow Pulsar. This neutron star doesn't just spin at dizzying speeds, it tears through space at 1,600,000 kilometers per hour, leaving a trail of destruction in its wake. That's fast enough to cross the entire United States in just 2 seconds, a velocity so staggering it could only come from one thing: a supernova kick so violent it turned this dead star into a runaway bullet. The story begins with the pulsar's birth, when its progenitor star exhausted its nuclear fuel and collapsed in a cataclysmic explosion. Most supernovas eject their remnants symmetrically, but this one was different, a lopsided detonation that launched the newborn neutron star like a cosmic cannonball. The recoil was so intense, it gave the pulsar more than just speed. It granted a death sentence to any star unfortunate enough to share its orbit, and that's where the horror unfolds. The Black Widow isn't traveling alone. It's locked in a lethal embrace with a companion star, a binary partner it's methodically evaporating. every rotation, the pulsar's intense radiation and particle beams bombard the smaller star, stripping away its atmosphere atom by atom. Telescopes detect the carnage in real time, an eerie glow of ionized gas trailing behind the pair like a ghostly comet tail, evidence of stellar material being boiled off into space at nearly light speed. The numbers defy belief. The pulsar's magnetic field, 1 trillion times stronger than Earth's, accelerates particles to such insane energies that they literally sandblast the companion star's surface. This isn't just stellar erosion, it's annihilation via relativistic fury. The victim, once a sun-like star, has been whittled down to a fraction of its original mass, reduced to a smoldering core barely larger than Jupiter. Even now, it's losing the equivalent of Earth's mass every million years, a slow but inevitable demise. What makes this system even more chilling is its inevitability. The pulsar's gravity ensures the companion can't escape, forcing it into an orbital death spiral. As the victim star loses mass, the pulsar's gravitational grip weakens just enough to let it drift slightly farther away, but that only prolongs the torture, stretching the stellar execution over billions of years. Eventually, the companion will be completely vaporized, leaving the Black Widow alone once more, a silent killer drifting through the cosmos. Yet for all its violence, this system is a goldmine for astronomers. The evaporating gas acts like a backlight, revealing details about the pulsar's magnetic field and spin that would otherwise be invisible. The orbital decay provides a precision test of Einstein's general relativity, while the sheer speed of the pulsar's proper motion offers clues about how supernova explosions can impart such extreme kicks. The Black Widow reminds us that the universe's fastest objects aren't always solo-speed demons. Sometimes they're predators, dragging their victims along in a high-speed dance of destruction. It's a cosmic cautionary tale, proving that in the race for velocity, not all competitors survive the finish line. While most spacecraft we've discussed push the limits of speed, Voyager 1 holds a different kind of record, not for raw velocity, but for relentless endurance at a staggering 61,000 kilometers per hour. After 44 years traversing the solar system, this nuclear-powered pioneer became the first human-made object to breach the heliosphere in August 2012, sailing into the uncharted waters of interstellar space with 23 billion kilometers already under its belt. What makes this escape velocity so remarkable isn't just the numbers, it's the invisible barrier it overcame. The heliosphere is a vast magnetic bubble created by our sun's solar wind, stretching far beyond Pluto's orbit. Crossing its boundary meant punching through the heliopause, where the outward pressure of solar particles finally yields to the interstellar medium's denser cosmic rays. Voyager didn't just cross a line, it passed through a turbulent transition zone where solar and interstellar winds clash like ocean currents meeting at a continental shelf. The data it sent back from this frontier rewrote textbooks. At 18.5 billion kilometers from Earth, Voyager's instruments detected a 40-fold spike in galactic cosmic rays, while solar particle counts plummeted, conclusive proof it had left the sun's protective bubble. But here's the cosmic irony. Even at its phenomenal speed, Voyager's journey had only just begun. Interstellar space isn't empty, it's a diffuse soup of ionized gas and dust, with plasma densities 1,000 times thinner than the best laboratory vacuums. Moving through this near-nothingness at 61,000 kilometers per hour, the probe collects data on magnetic fields and particles that sunlight will never touch. Consider the scale of this achievement. Launched in 1977 to study Jupiter and Saturn, Voyager 1 outlived its original mission by decades. Its cameras were turned off in 1990 to conserve power, yet its other instruments continue operating today, each watt of electricity carefully rationed from decaying plutonium batteries. The signals it beams back take 21 hours to reach Earth, so faint that NASA, a deep space network, must filter them from background noise with antennas the size of a 20-story building. Yet for all its solitude, Voyager carries a piece of humanity into the void. Its famous golden record, a 12-inch gold-plated copper disc containing sounds, music, and images of Earth, may outlast our civilization. While the probe itself will go silent around 2230 as its power runs out, its trajectory will continue indefinitely, passing within 1.6 light-years of the star Gliese 445 in 40,000 years. What's often overlooked is how this journey redefines speed's cosmic context. Voyager's velocity, 17 kilometers per second, seems sluggish compared to hypervelocity stars or pulsar jets. But unlike those natural phenomena, this speed is sustained. No gravity assists, no explosive acceleration, just the steady push of its 3 radioactive batteries, maintaining momentum across light years where even light feels the drag of interstellar medium. The probe's exit also gave us an unexpected gift, the first true measurements of our solar system's shape. Contrary to early models suggesting a comet-like tail, Voyager revealed the heliosphere is more like a blunt bullet, flattened on one side by the interstellar wind's pressure. This discovery alone reshaped our understanding of how stars interact with the galaxy at large. Now drifting through what astronomers call the cosmic shoreline, Voyager still transmits its speed, ensuring it penetrates ever deeper into territory where the very definition of space changes. Ahead lies the Oort cloud, a hypothesized shell of icy objects marking the solar system's true edge. Voyager won't reach its inner fringe for another 300 years, nor escape it for 30,000. A reminder that even our fastest creations are slowpokes in a galaxy where distance humbles all velocities. Some planets don't just orbit stars, they flee from them at speeds that defy gravity itself. Take CFBD Sir 2149-0403, a rogue world hurtling through interstellar space at 540,000 kilometers per hour, so fast it could cross the entire solar system in under 2 weeks. This isn't just drifting, it's full-blown cosmic eviction, an exile so violent it raises the ultimate question. Was this object born a planet, or is it something far stranger, a failed star banished from its own system? The evidence is as puzzling as the planet's speed. Discovered in 2012, CFBD Sir 2149 appears to drift alone in the darkness, untethered to any star. Infrared telescopes reveal it's surprisingly warm for its age, around 400 degrees Celsius, with an atmosphere rich in methane and water vapor. At 4 to 7 times Jupiter's mass, it straddles the blurry line between planet and brown dwarf, those strange substellar objects too small to ignite sustained fusion. This ambiguity is key to its origin story. One theory paints a dramatic picture. This world began life as a gas giant orbiting a young star until gravitational chaos kicked it into the void. Simulations show that in crowded multi-planet systems, close encounters between massive worlds can slingshot one member outward like a cosmic pinball, sometimes reaching speeds high enough to escape the star's grip entirely. The numbers add up. At 540,000 kilometers per hour, CFBD Sir 2149 moves faster than most star systems' escape velocities. It's the astronomical equivalent of a car tire flying off at highway speeds, except here, the tire weighs several Jupiters and the highway is the Milky Way. But there's a twist. Some astronomers argue this object isn't a planet at all, but a solitary brown dwarf, a star that never quite made it. Brown dwarfs form like stars, collapsing from gas clouds, but lack the mass to sustain hydrogen fusion. If CFBD Sir 2149 formed this way, its loneliness wouldn't be banishment, just bad luck, a stellar embryo born without siblings. Supporting this idea are spectral signatures typically seen in brown dwarfs, not planets. The debate hinges on definitions. Is it a runaway planet or a stellar reject? Nature, as usual, resists tidy categories. What's certain is this object's journey holds secrets about galactic demographics. Rogue planets, if that's what it is, might outnumber stars in the Milky Way. Current estimates suggest billions could wander the darkness, ejected during their system's chaotic youth. Some could even harbor subsurface oceans, kept liquid by radioactive decay or tidal heating, making them potential oases for life in the interstellar desert. On the other hand, if CFB Sir 2149 is a brown dwarf, its existence challenges models of star formation. Isolated brown dwarfs shouldn't be this common. Their typical birthplaces are dense stellar nurseries, not the empty void where this one now roams. Its discovery hints at unseen populations of free-floating substellar objects drifting undetected between the stars. The truth might lie in motion. Future telescopes could measure CFB Sir 2149's trajectory with enough precision to trace its path backward, like rewinding cosmic security footage. If it points to a known star-forming region, that favors the brown dwarf hypothesis. If it leads to a mature star system, planetary ejection becomes more likely. Until then, this speedy enigma serves as a reminder. The universe doesn't just create worlds sometimes, it flings them into the darkness with unimaginable force. The universe's speed limit, light's unbreakable 299,792 kilometers per second, is a rule so fundamental we've built modern physics atop it. But what if particles exist that laugh in the face of this cosmic speed limit? Enter tachyons, hypothetical entities that don't just approach light speed, they start beyond it, forever racing faster than causality itself. The math allows it. Special relativity prohibits accelerating objects to light speed, but doesn't forbid particles born faster than light. These phantoms of quantum theory would behave unlike anything in our universe, their energy decreasing as they speed up, requiring infinite energy to slow down to light speed. Imagine a cosmic speedometer running backward. The harder you press the brakes, the faster you go. The implications shatter our understanding of reality. If tachyons exist, they'd warp causality into pretzels. Their superluminal speed could let them arrive before they depart, creating time loops where effect precedes cause. A tachyon signal sent to a star system 10 light-years away might reach its destination 9 years in the past, appending the very notion of sequence. This isn't just theoretical wordplay, it suggests phenomena like quantum entanglements, spooky action at a distance, might harness hidden tachyonic layers where information bypasses spacetime strictures. Then there's the Opera experiment's infamous 2011 anomaly. CERN scientists reported neutrinos, those ghostly, nearly massless particles appearing to outpace light by 60 nanoseconds. The physics world erupted. Had we accidentally detected tachyonic behavior, the frenzy ended when a loose fiber optic cable was found skewing the timing data. But the episode revealed how tantalizingly close we've come to testing these ideas. Modern neutrino observatories like IceCube now routinely monitor for anomalies that might hint at superluminal loopholes. Critics argue tachyons are mathematical curiosities with no physical reality, that their existence would enable paradoxes like sending messages to kill your own grandfather before your birth. But supporters counter that quantum fields might naturally contain tachyon-like excitations, with the Higgs field itself briefly behaving this way during the early universe's phase transitions. Some interpretations of dark energy even cast it as a cosmological tachyon field, its repulsive gravity accelerating the universe's expansion, the wildest possibility. Tachyons might not be particles at all, but disturbances in spacetime's fabric, kinks in reality's structure that propagate faster than light without carrying information, preserving causality while bending the rules. Until we detect one or disprove their existence, tachyons remain the ultimate cosmic speedsters, not just breaking records, but rewriting the rulebook of physics itself. From light's unbreakable 299,792 kilometers per second to rogue planets hurled into the void at 500,000 kilometers per hour, we've raced through 30 cosmic speed records that redefine what fast even means. These aren't just numbers, they're the universe's way of showing off. pushing physics to its limits in ways that leave our human-scale intuition in the dust. Think about it, a hypervelocity star blasting out of the Milky Way at 1.7 million kilometers per hour feels impossible until you realize it's just another Tuesday near a supermassive black hole. Or consider the pulsar spinning 43,000 times a minute, where the surface moves at nearly a quarter light speed. Proof that when gravity and angular momentum team up, they don't play by our rules. Each record we've explored reveals something profound about the cosmos. Light speed isn't just a limit, it's the universe's clock, shaping causality and stitching space-time together. The Bullet Cluster's 10 million km/h collision exposed dark matter's invisible hand, while gamma-ray bursts like GRB 080319b showed us particles surfing shockwaves at 99.9999% light speed. Even the humble Parker Solar Probe, humanity's fastest invention, hits 700,000 kilometers per hour yet still moves at a cosmic snail's pace compared to stars like S4714, whipping around our galaxy's black hole at 8% light speed. What's truly humbling is how these extremes force us to rethink scale. A neutron star merger's ejector at 30% light speed seems unfathomable until you realize it's sprinkling gold across galaxies, meaning the ring on your finger might owe its existence to physics more violent than any sci-fi. The Hubble constant 73 kilometers per second per megaparsec seems abstract until you calculate that galaxies beyond our local group will eventually vanish over the horizon, racing away faster than their light can reach us. Speed isn't just motion here, it's the universe's language for creation, destruction, and transformation. So where does this leave us? Probably somewhere between awe and hungry curiosity. If hypervelocity stars, rogue black holes, and galaxy-scale shockwaves exist, what undiscovered extremes lurk in the voids between superclusters or the hearts of quasars? Could quantum foam hide particles that cheat light's limit, or will we find structures so vast their proper motion defies relativity? The cosmos loves breaking its own records, and every discovery starts with someone looking up and wondering, what if? Now it's your turn. Which of these cosmic speed demons left your jaw on the floor? Was it the Black Widow pulsar vaporizing its companion at 1,600,000 kilometers per hour, or the Magellanic Stream's gas racing around the Milky Way like a celestial river in overdrive? Drop your favorite in the comments or hit subscribe to join us as we hunt for the next universe-shattering record. Because in a cosmos where even impossible speeds are just another natural phenomenon, the only real limit is our imagination.